All right, so we're starting our first unit. This unit is on kinematics, and we're looking at how can we describe the motion of objects. So motion is a very complicated phenomenon. If you think about things moving, can be a lot going on there depending on the motion. So as scientists, as physicists, we want to start by trying to break it down to its most simple situation that we can get. So that simple situation in this case would be just an object that's moving in one direction at a constant speed with nothing else going on. So here we're going to be looking at this little toy car I've drawn. We're going to be saying, okay, this car is moving along at a constant rate. How can we describe that motion? How could we represent it? How could we create a model? Because that's what science is about. Science is about creating models, mathematical models, to help us break down a physical phenomenon or a physical situation. So we're going to look at how can we break down mathematically, how can we represent the motion of this toy car as it moves in one dimension at a constant rate. So the first thing to think about is how can we describe this motion? What words could we use to describe the motion of this buggy, of this toy car as it's moving along? How could we describe it? And the first thing that comes to mind is talking about its location, where it is. And so in physics, we're going to use a specific vocab word for that location, and that word is position. So here's our definition of position. Position is the location of an object compared to a previously determined origin point. And it's a vector quantity. We'll get to that in a second. So when talking about where something is, we need to have a reference. I can't just say I'm at 2 meters. 2 meters from what? So whenever we're deciding the position of an object, first thing we need to pick is we're comparing that position to where. So in this case of the buggy moving around, moving forwards, I'm just going to say, makes sense to start where my zero position, I'm going to say, is the very front of the buggy at the start of the motion here. So I'd say that's going to be my origin point, my zero position. And then as the buggy moves along, I'm going to say it's moving in the positive direction because it makes it easier to think about it that way, to say, okay, so this buggy's moving. I'm going to say 1 meter is over here, 2 meters, 3 meters. And this isn't just 2 meters, this is 2 meters to the right of my zero position. And we'll call this the positive direction. So I'll draw an arrow to show. That way is where I'm saying positive direction is. So as the buggy moves along, I would say, okay, after a certain amount of time, it's 1 meter to the right, or 1 meter in the positive direction from the origin. And then it's 2 meters, 3 meters, and so on as this buggy is moving. Now, if the buggy, went in reverse, maybe I would have to worry about, okay, continue this line over here. Not going to get that exact, but maybe it starts moving in the negative direction, but we'll worry about that at a later time. All right, so that's its position, where it is located to this origin. And this origin point I chose was completely arbitrary. I could have made the zero position somewhere over here. Let's see what that would look like. Let's grab this extra copy. Bring it over. I could have said, you know what, over here is 0 meters, where I have the 2 in my other situation. And so this would be, and I'm still going to say to the right is the positive direction. So that would make this negative 1 meters, and the buggy would be starting at negative 2 meters. So both of these would be valid ways to mark an origin and mark the position of the buggy. And we'll see as we go along that all the stuff we do, it ends up working. It looks a little different, obviously, right here. The buggy's starting at 0, here it's starting at negative 2, but it will all work out. So don't fret too much about your choice of origin point. It's all going to work out either way. All right, so this is the location of the object, and it's a vector quantity. It includes both direction and size. So in this case, I would say my buggy is 2 meters. That's my size. That's how far, 2 meters in the negative direction. So negative 2 meters would mean over here. Positive 2 meters would mean somewhere over on the other side there. So when we're talking about position, we're giving both the distance, how far, and the direction, which way. So here my buggy is 2 meters to the left, which I would represent by negative 2, because I'm saying positive is to the right. All right. Okay, so now what we're going to create, as this buggy moves along, it's going to change its position. It's not going to keep this position. As it moves, that position is going to change. And to help us interpret that, we're going to create a picture or a model known as a motion diagram. So what I'm going to do is I'm going to watch this buggy move, and every instant of time, let's say every second, I'm going to mark down where the buggy is. So this buggy is a three-dimensional object. I've drawn it 2 dimensions, but so it has a bunch of different spots. So I'm just going to pick a spot on the buggy, and I'm going to pretend the buggy is basically just at that one point. I'm going to pretend it's basically a particle, one point in space. And since I've made the origin the front of the buggy here, I'm going to use that as my point. So I'm going to say at 0 seconds, my initial time, the buggy is at the origin. And then let's say I follow this buggy and I find out 1 second later, it's here. And then another second later, so this after 1 second, the buggy's front would be there. 2 seconds, it's here. 3 seconds, it's there, and so on. So this is me creating a motion diagram of this buggy, marking its position at each instant in time. In this case, I've chosen those time intervals to be every second. All right, so I could say for this buggy, I could talk about its position at 0 seconds. It's at, and we're going to use the letter X when we talk about horizontal position in this case. So its position at 0 seconds. So when my time equals 0, my position is 0. My time equals 1 seconds. My position is, looks like I'm at about half a meter here. And so on. I'm going to skip the 2. I'll go straight to the 3 here at 3 seconds. My position is, looks to be at 1.5 meters. If you wanted to, at t equals 2 seconds, we can see it's exactly at 1 meter. Okay. So if I was just thinking about the start versus my ending time here, I could label these. I could say this is my initial time. My initial time is t equals 0, and my final time, 3 seconds. I could say my initial, this should be meters, wow. Say my initial position is 0, and my final position is 1.5 meters. Okay, so that is time and position in using a motion diagram. We could do the same thing here. Let's say it's the same buggy doing the same motion. So at 0 seconds, it's here. 1 second, 2 seconds, 3 seconds. And we'll notice we get different position values here, right? At t equals 0 seconds, my initial time, my buggy is at -2 meters. And then at 3 seconds, my final spot, my buggy is -0.5 meters. So yeah, we chose a different origin here. We just made the origin point somewhere to the right. So we do end up with different position values, and that's okay, because these were all just relative to the point we had picked. We're still describing the same motion. We're still describing the same buggy moving at this constant rate. There's another word we're going to use in relative to position, and that word is displacement. Displacement is the change in position over a certain time interval, all right? So the displacement of the buggy, let's write down that definition real quick here. So we've got displacement is the change in position. And written mathematically, we use this triangle symbol called delta. So delta x is change in x being position. So change in position is just the final position minus the initial position. And we can see that here if I started at 0 and I ended up at 1.5 meters, well, my displacement, my delta x here, would be, well, I ended at 1.5, I started at 0, so my displacement, I've gone 1.5 meters in the positive direction because it's a positive 1.5, so I'm 1.5 meters to the right from where I started. You could see again, if we had chosen a different coordinate system, our delta x would be our final position, negative 0.5 meters, minus our initial position, which was negative 2 meters. Well, minus minus, it ends up being plus, so negative 0.5 plus 2 is positive 1.5 meters. And this is why our choice of origin ends up not mattering too much, because when we look at the displacement, how far we are from where we started, well, it ends up being the same either way. Now, this is probably the smarter place to put the 0 position because it makes sense logically for our starting point to be our 0 point. But this works just as well. It gets us the same displacement, the same change in position, because it's still the same motion. We've just measured it a little bit differently. All right, so that's one way we can represent motion. We can represent it through this idea of the motion diagram, or you might hear this referred to as a motion map, where we mark sort of like a freeze frame, like we were taking a picture every second of where this buggy is. That's one way we can represent its motion. We'll see for something moving at a constant rate that these dots end up being evenly spaced from one another. It goes the same displacement in these equal intervals. Now, another way we could represent the motion is by graphing it. And we can graph, we have two things here. We have position and we've got time. So we can graph the position and time of this buggy. I'm going to label these. I'm going to label this situation 1 and this situation 2. I mean, they're the same situation, but different ways of measuring it. So let's graph what it would look like if we had measured it the first way. So we're going to have position and time, because those are the two things we were able to measure about this buggy. Time's going to go on the x-axis and position is going to go on the y-axis. That might feel a little weird because in math classes you've probably done a lot of putting calling this the x. So that's one thing to look out for. Is here x is talking about position, it's not talking about our x variable. Here the x variable is time. So we got position and time. And I can just go and mark 1 second, 2 seconds, 3 seconds, 1 meters, 2 meters. We don't need it for this one, but -1 meters, -2 meters. Always good to draw the 0. So here we have 1 meter, 2 meter. Technically I don't have to put the m's here because I put m here, but why not have it in both places? And we have 1 second, 2 seconds, 3 seconds. And now I'm just gonna straight up use my dots on my motion diagram to fill in my graph here. So at 0 seconds, I'm at 0 meters, easy. At 1 second, I'm at ½ a meter. 2 seconds, I'm at 1 meter. I'm just going to zoom in and get these down. So it's at ½ a meter, 1 meter. 3 seconds, I'm at 1.5 meters. And we'll see that that makes a, obviously I'm not perfect at drawing it, but you get a nice straight line. This would be my position versus time. A couple of things we can see here. My displacement, my change in position, would be the rise of this graph, right? That's how far I go up in the 3 seconds. My run would be my time interval. In this case, my time interval, my delta t would just be 3 seconds because I started it at 0 seconds. So 3 minus 0 gives me 3. So 3 seconds, and we calculated this before, was 1.5 meters. I'll see if I draw this the situation 2-way, where I had my origin arbitrarily chosen to be somewhere to the right, that I am going to get a slightly different looking graph. So again, I'm going to have 1, 2, 3 seconds. So here we have time in seconds, position in meters. Here's my 0. 1, 2, -1, -2. Here, my starting position at 0 seconds, I was at -2. 1 second later, I was at 1.5. 2 seconds later, oops. 2 seconds later, I was at -1. And at 3 seconds, I was at -0.5. So you see these graphs do look different. But if I looked at my displacement, that'd be the rise here, I'm still going up. If you want to remind yourself that going up plus 1.5 meters and my run is still my delta t, still 3 seconds. So we'll see, again, no matter how we had picked our origin point, we end up with some similar information on both these graphs. Yep. Rise of 1.5 meters over 3 seconds. So that's another quantity here. We have this graph, we have the points on the graph, and then we also have a slope. We can see that these graphs, they share the same slope, and that slope is a very important measurement, something you probably have been wanting to say for a while. That's talking about how fast we can think this buggy is going. That's the rate of change of its position over time. If I look at the slope of this graph, I can find that this buggy is moving 0.5 meter every second. So I know slope, rise over run, and slope is the rate of change. It's how position is changing over time. That's going to be a really key word that we're going to use. That's the velocity of this buggy. The buggy's velocity is the rate of change of its position with respect to time. So here's that definition for you. It's a calculation of the rate of change, and we're going to calculate it by just using, in this situation where the buggy is going at a constant velocity, where this slope is the same everywhere, right? This is a straight line, it's not curved, it's not a quadratic or anything. So the slope stays the same. It's the same change in position over change in time everywhere. So that makes it very easy to calculate. We're just going to do the rise over the run. So our velocity, which we represent with the letter V, we can do 1.5 meters over 3 seconds, 0.5 meters per second. Notice this is a positive value at a positive slope because my buggy was moving in the positive direction. It was getting 0.5 positive meters every second. Same deal here. Well, notice, even though I chose a different origin, that my velocity is still 1.5 meters over 3 seconds, 0.5 meters per second. So it was moving in the positive direction and changing by 0.5 every second. So even though it was at a negative position, its velocity was positive. It was moving in the positive direction. So negative position, but positive velocity. Because in either case, we have the same slope, the same change in position over time. There's another graph we can now do, and that is the velocity versus time graph. Now, in the case of this buggy moving at a constant speed, speed, by the way, speed is the magnitude, the size of the velocity. So I would say the speed is 0.5 meters per second. The velocity is 0.5 meters per second. to the right. So again, velocity has both a direction and size. So it's 0.5 meters per second. The direction we could say is the positive direction, or you could say, given our picture, you could say to the right, because we said to the right was the positive. Other words we could use for direction would be north, south, east, west, things like that, depending on the situation. And this would be the speed, 0.5 meters per second. If something was moving to the left at 0.5 meters per second, I would say it has a speed of 0.5 meters per second and a velocity of negative 0.5 meters per second. Okay, so our other graph we can now do is we can talk about velocity versus time. Seems a little silly to do when we know the velocity isn't changing, but there's going to be some important things it's going to show us that's going to be very relevant later when we get to situations where we don't have a constant velocity. So let's say I wanted to graph the velocity versus time. And here's where it's going to become very important as we dive deeper into physics to pay real close attention to our graph labels. All right, so here, position versus time. Now we're doing velocity versus time. This is going to be for the same object, the same motion, but these graphs are going to look different from each other because this one is velocity and this one is position. All right, so again, I could have a positive velocity if I'm going one way and a negative velocity if I'm going the other. So I'm going to include both the positive and negative. Notice we're never going to have a negative time, so we're not going to have those quadrants. We're only going to be dealing with these two quadrants when talking about velocity or position. All right, so I look at the slope here, and the slope is the same the whole time, and I found it was 0.5 meters per second. So let's say that this dash I made here is 0.5 meters per second. This would be 1 meter per second. And that velocity is unchanging, so it's just going to be a straight line going across there. We can throw some 1 second, 2 second, 3 second on here. All right, so that would be the velocity versus time graph. And notice, well, this is the same unchanging slope. The velocity graph is exactly the same for both of these. So this is the velocity graph for 1 or 2. Turns out it doesn't matter where we picked our origin to be, we end up with the same velocity graph because they both end up with a constant velocity of 0.5 meters per second. So this graph is kind of cool. It shows us velocity, it shows us time. We can see the velocity is staying the same. There's no slope here, right? There's no rate of change of velocity over time. We have the same velocity the whole time, no slope. Now, we've kind of lost something. This graph, I could see the position, I could see the displacement, I could find the velocity by looking at the slope. Here I'm only seeing velocity and time. So is there a way for me to somehow get some information about position here? And there is. If I look at this shape, you can see I have sort of a rectangle going here, where the height of the rectangle is my velocity. And let's say the time I'm looking at is the full 3 seconds here. That's my delta t. Those make an area. I have a height and a base. So velocity v times delta t can give me delta x. And you can look again back up here where we did velocity was rise over run. I was doing, we skipped writing it, but that was doing velocity is change in position over change in time. So now if I just sort of rearrange that formula, if I multiply the t over, I can get delta x equals velocity times delta t. And again, I really want to stress this only works, this formula worked, rise over run, because this is a constant slope. We can only do this because this slope is not changing. That's the only reason we can do rise over run. Okay, so position, change in position, that is displacement, is v delta t. And that would be the area of this rectangle, right? Base times height, or base times height, delta t times v. So on this velocity graph, I can see displacement as the area, what we would call the area under the curve. So I can see if I'm going at 0.5 meter per second for, let's say, 2 seconds. So I'm only worried about the area up to 2 seconds. 0.5 meter per second for 2 seconds, that's, I go 1 meter. And that would be the area here. 2 times 0.5 would give me a delta x of 1 meter. So that's how we can use the velocity graph to learn a little bit about the displacement. Notice this tells me the displacement. This does not tell me, I do not know where this object is just looking at this. All I know is when it traveled for these 2 seconds, it is now 1 meter further in the positive direction. Great. All right, a little exercise for you, the viewer, is to try to now make a graph for a new object. Let me give you that new object. Let's do, I'm just going to erase this stuff here. Let's say I have another buggy. And let's extend this line a little bit to 4 meters. And let's say this buggy, it's going to be a blue buggy. Good enough. And this blue buggy, say, is starting exactly at the 4 meters. Use the front of the buggy again. So at 0 seconds, it's here. And let's say the buggy is moving to the left in this situation. So after 1 second, 2 seconds, 3 seconds, at the 4th second, let's meet it to that 3 meter mark. Try now, you can pause the video, try to draw a position versus time graph and a velocity versus time graph for this buggy. And then at the end you can go, maybe you fast forward down this video, I'll have the last part be both those graphs, or you can then follow along and see if what I do agrees with you. All right, so I'm going to start with our position versus time graph. I see that this buggy is not going to be in it. I'm going to move this down a little bit, give myself some more room. So time in seconds and position in meters. Make sure I get to 4 meters here. And time 1, 2, 3, 4 seconds. All right, so at 0 seconds, we're at 4 meters. And I'm going to skip ahead. I see this is a constant rate. At 4 seconds, we're at 3 meters. And I could fill in those other points in between. But I know it's going to be a straight line because I can look at this motion diagram and I can see every second the buggy has moved the same displacement. It's changed its position by the same amount. This would be at 3.25. This would be at 3.5. This would be at 3.75. So that would be my position versus time graph. And looking at this, I could find my displacement. My delta x is x final minus x initial. And I can see here I have a negative displacement. My buggy is now more negative than it used to be. It started at 4, now it's at 3. So 3 minus 4, negative 1 meters. Now again, this doesn't mean it has a negative position. It still has a positive position. It's still 3 meters to the right of the origin here. But its displacement, its change, was negative. It moved in the negative direction. So that's my delta x. And my delta t was 4 seconds. So I could find velocity is negative 1 meter over 4 seconds equals 0, negative. Very important, because velocity has direction as well. Negative 0.25 meters per second. So my speed, 0.25 meters per second. My direction is to the left in the negative direction. So my velocity has both the magnitude 0.25 and the direction negative, because that's all that negative or positive mean when we're dealing with kinematics, when we're dealing with motion. They just mean a direction. So negative versus positive, no, neither one's better or worse than the other. It just means which way you're going. Some things to note, I didn't have to use the whole interval here to find this. I could have just looked at the first second, because it is the same velocity throughout. Again, we have this easier case, same slope everywhere, delta x over delta t. Whatever deltas I choose, I could just do this delta x and this delta t. I get the same velocity because we're dealing with a constant velocity model here. So let's make a velocity versus time graph for this. Velocity meters per second, time in seconds. So again, by including the units here, I don't have to draw them with these numbers. Still a good idea though. I just don't have room. Okay. Ooh, so a quarter. This would be half. There's a quarter. And notice now I'm on the negative part of the graph. Always, always, always a good idea to put your 0 point on the graph. All right, it's a little crooked, but we're good there. All right, so that would be my velocity. 1, 2, 3, 4 seconds over those 4 seconds. Again, I could find my displacement, my delta x. We know what it is, but if I wanted to, I could find it. I know this is 0.25. 0.25 meters per second. Try to shrink this a bit and we can fit it in there. There we go. And my displacement over the 4 seconds would just be the area. Now I don't have to do the full force. Maybe I wanted to know how fast, how far it changes its position from the first to the 3rd second. So in that time interval, maybe I want to know what was its change in position, in which case I would just look at the area. And I know we called this earlier the area under the curve when we were doing it. Or were we doing it right over here? In this case, we're taking the area upwards to the, so we're always doing the area to the axis line, because again, we have this idea of we're doing the time, delta t. So in this case, 1 to 3 seconds, the delta t of 2 seconds. And the height of this rectangle would be 0.25. So From the first to the third second, this object undergoes a displacement of 2 times 0.5 is 0.5, negative 0.5 meters. So it travels in the negative direction, is 0.5 meters more in that direction. Doesn't mean it's at a negative position now, it's just traveled in the negative direction, 0.5 meters. And that's model 1.